Hi everyone, welcome to RPI Data Science. Today I would like to talk about regularized regressions. So up to now we have seen naive Bayes from quantitative text models, and also we have already seen support vector machines, mainly linear SVM from quantitative text models, and then we move to E1071 package, and we have seen different SVM models depending on the kernel parameter choices. So we have seen linear SVM, radial SVM, and also we have seen sigmoid SVM. So these support vector machines, they are known for taking care of this high dimensional data such as text and genetic data, which in fact you have more number of features and than number of observations. So the number of features or the number of variables is very high. So it's really high dimensional data. So so we have already seen support vector machine, which is very effective in dealing with this kind of high dimensional data. But there is another sort of algorithms in our toolbox, and this is regularized regression models. So today we will go into the details of regularization models. The best way to understand the regularized regression models is actually to have a basic understanding of linear regression. So if you know the ordinary least square regression, so in this example, for example, the sales price as a function of the living area. So this is a house sale data, house price data. So this is the sale price. The sale price as a function of the living area. That means the size of living area in the room. So the more the size of the living area is, so the more expensive the house is. So when you look at this, so you feed regression model, and the goal of your regression model is to be able to predict the observed values as efficiently or as effectively as possible. So that means the error or the distance, the distance from the observed value until the predicted value should be as minimum as possible. So that means you have the best hyperplane. Hyperplane. So we have already talked about hyperplanes in support vector machines, and this is nothing different. They are more or less similar concepts. So when you look at the individual values like this, so for example, there is an observed value here, but the predicted value is down here, and you have another value here, and the predicted value is here, the observed value is here. So your goal is to reduce this error. That means the error from this point until here, and then from this point until here. That means from the predicted value, from the observed value until the predicted value, and that's called the error. So your objective function or your loss function is sum of square errors, which is calculated by a different formula. So we will see the objective function or the loss function in this case is sum of square error, and your wish is to minimize this error. That's what you want to do in your ordinary least square regression model. And the error between the predicted value, the distance, the error is the distance between the observed value and the predicted value, and which is calculated by sum of square errors formula, and that is the observed value minus a predicted value. You square it, and that means from I to n, because we have many observations until n, and that's what sum of square tells you. But the problem is this linear ordinary least square regression works very well for most of the cases, but the problem is it requires assumptions. So linear models are very effective, and it works for most of real world contexts, and it's simple. One of the most powerful aspect of the linear models is simplicity. So it's simple and effective, and usually computationally not very expensive process to do ordinary least square regression models. However, the objective function that we have seen, sum of square error, requires key assumptions. So these assumptions need to meet for your linear to ordinary least square regression model to be effective, or to be working. Otherwise, it will lead to erroneous predictions. So these assumptions are, one of the assumptions is linearity and homogeneity of variance. So that means the variance need to be homogeneous. And the last one, there are many others, but these are the three main assumptions, and it requires you need to have more observations than number of features, which means you need to have more number of observations than number of variables. So the problem is with today's data is usually, mostly high dimensional. If you look at text data, or if you have genetic data, you have more number of features than number of observations. Yeah, so if these assumptions are met, that means the estimated coefficient in your ordinary least square regression are unbiased, and you will have a small standard errors, and that means your coefficient has a smaller variance, and that means the value of the coefficient is more accurate, and then that means you can predict the value closely as the original, as the observed value. That means your prediction model is working well. The problem, as I said, this linear ordinary least square regression model, it works very well, but the problem is when you have more number of features than number of observations, for example, in genetics and text data, then you have a problem. So for that, you need to find a solution. There are many solutions, and one of the solutions is feature selection strategy. So you try to select the important features, and you remove the features that have zero cells, for example, or the features that you believe they are not important, or depending on your literature or something. That means you are betting on sparsity. The sparsity, we have already talked about sparse data in the past. So sparse data is something really large data which has zero values, or maybe doesn't have much weight or much a number of values in your data set. So that means this kind of data, you trim it or you cut it out from your analysis. That means you are betting on sparsity. There are two techniques of feature selection methods, and one is hard thresholding. And if you already know, if you are familiar with ordinary least square regression, I'm sure you know about forward selection and backward elimination methods. These methods, they work very well for ordinary least square regression, but whenever you have such a large, such high dimensional data, that means you have a high number of features, and you may also have still longer, bigger number of observations, but still your number of features should be as very high. So in that context, this hard thresholding method is not efficient. It's computationally inefficient, and that problem is it doesn't scale well. If this happens, that means your coefficients will fluctuate and your prediction will be wrong, will be erroneous. So you try to find another solution, and that's the soft thresholding method. And this soft thresholding method is a regularization technique. What it does is it slowly pushes the effect of irrelevant features towards zero, or in some cases it will zero them out, and then at the end you will only have the only relevant features. At least the second one is in LASSO, but the first one is in ridge regression. So that means all the coefficients or the irrelevant coefficients are pushed toward zero, but not all the way to zero in terms of ridge regression. But in terms of LASSO regression, they will be zeroed out, and all the irrelevant features will be removed. We'll come back more in these points in terms of ridge and LASSO regression details. So this techniques is computationally efficient, and it also reduces the fluctuations on coefficient values, and the variance of the model coefficient will also be more stable. So that means your prediction will be more accurate. Yeah, so as I said, the objective function of ordinary least square regression is to minimize the sum of square errors, but in this case, in regularized methods, you add additional penalized term. So you add another error term on the already the sum of square errors. And this is already the sum of square errors. On top of that, you add another error, and your objective function is nothing different but similar to the ordinary least square regression model, and you try to minimize this error as possible, as much as possible. So how is this error term calculated? So we have said this is the error terms that we have added. So this is a penalty term. But how do you calculate it? This is calculated depending on the choice of your regression model, depending on the choice of your regularized regression model, actually. So that means if you choose REACH, and you may also choose LASSO, and then at the end you have ElasticNet. But there are other choices, other models, but at least these are the most common regularized regression models. And they can be applied to logistic regression principles, or they can be applied to regression methods. So that REACH can be classification, but it also regression. It's an algorithm that you can use to take on classification task or regression task, and all of them can be applied to either classification or regression problems. In terms of REACH regression, for REACH regression, what you do is the formula for the error is calculated by this lambda times the summation of the coefficients, the square of the coefficients, which is for each of the features. That means from feature number 1 until the last feature. So that means you added this term. This is actually called the Euclidean norm, and your goal is again to minimize this error. So you can think when lambda is 0, when lambda value is 0 here, so that means this will be zeroed out, and then your regression model will be the ordinary least square regression model. That means in your ordinary least square regression model, it's still, this is zeroed out, and that's because your lambda value is 0. So, but now this is when lambda is 0. But what if lambda is going more than 0, or from more 0 point something to infinity? What will happen? So what happens is when lambda is greater than infinity, when lambda is going to infinity, that means, let's say in this case, these guys, they have added 15 variables from variable x1 until many different variables. So that means when lambda is approaching to infinity, that means the value of the coefficient is pushed toward the 0. It's pushed toward the 0, but it will not touch it at some point in infinity. It's simply approaching it, but it will not really touch it. But it's getting closer and closer. So let's say in this REACH regression model, so you have from lambda from 0, actually from more than 0 until approximately 1000. So when you look at these variables, for example x1 and x4, you see x1 is a bit, it doesn't have like the way it's moving, it doesn't look like that it's stable. It's fluctuating. So for example, you see when your lambda value is close to 0, it started somewhere in negative 7.5 or something, and then when your lambda value is going somewhere around 7, then your coefficient, the beta coefficient for this x1 is going into close to -10, which is somehow large. But the value of this coefficient is really oscillating. So it started somewhere from minus, and then it goes to minus around -10, and then it's moving towards 0. So whenever you have this kind of fluctuations, that means there is a multicollinearity problem. So that means there is multicollinearity problem. What ridge regression does in this condition is when, let's say, when x1 and x4, in this case actually they look like they are correlated, they look like they have multicollinearity variables because they also cross, and then what it does is it tries to push one of the coefficients. I mean, both of them will be pushed to 0 at some point in infinity, but at least one of the coefficient will have a wildly negative coefficient, where the other one will have a wildly positive coefficient. So ridge regression models push many of the correlated features towards each other, rather than allowing for one to be wildly positive and the other one to be wildly negative. And so less important features will get pushed towards 0, but not all the way to 0. That means the less important features, they will approach 0 value, but not all the way to 0. That means they will not really be completely vanish from our model. So the ridge regression at the end, it will retain all your variables, and it doesn't provide feature selection method. So that means because all your variables, they are all gonna be retained at the end of your model procedure. So that means all variables will appear in your final model. So that means ridge regression is not a model for feature selection. You either need to select beforehand, or your wish should not be, your goal should not be on retaining relevant features or something. Your wish may be prediction, just a prediction task, not the variables that are important or associated to something or something like that. Your wish here should be just a prediction, but still you need to determine what kind of data and in what kind of situation that you can fit ridge regression model. So when to use ridge penalty method? It's when you have smaller data set with severe multicollinearity issue, because as we said, one of the coefficient, when you have multicollinearity, one of the variables will be pushed to 0, but the other one will stay in the model, will still have higher coefficient, at least when you have this kind of situation. So one will be approaching to 0, and the other one will have some higher coefficient value, either negative or positive, depending on the relationship of the variables. And if you need greater interpretation, and if features are redundant, if your goal is to have a greater interpretation, that means to have list of variables that are important for your outcome, or if features are redundant, that means one feature is the information that is already in one feature, if it is in another, that means your features are redundant, or maybe one feature is derived from the other. So that means you have to find a way to avoid or to remove these irrelevant features. And for that task, LASSO or ElasticNet could be preferable choices. So now next we will talk about LASSO, and in a minute we will jump into ElasticNet. So as we said, for ridge regression, what you do is you have sum of square error, and then the error term is the square of the beta coefficients, and then the lambda value will stay the same, of course, and then from j to 1, and that's p. So that's for ridge regression. But in this case, for LASSO, what you take is you take the lambda and the summation of the beta value, the coefficient, the value of the coefficients will be in absolute value. So that means you will take the positive value of whether it's negative or positive. You will take the absolute value, and that's lasso regression. And of course, your goal is to minimize this error. So this is the same data set that is again fitting 15 different variables. So in this case, let's say when lambda value is approaching, when lambda value is around 0.01, that means all of the 15 variables are retained in the model. All of them are still in the model. And then you go somewhere here, for example, this is probably 0.05 maybe 0.05, and this is at 0.05 when lambda is 0.05. That means still all of the variables are still there, but some are approaching zero, some are really approaching zero. But when you go somewhere here, somewhere where lambda is 1, for example, some of the coefficients are really pushed towards zero, but there are others like x1 is still there, and this red one is still there. The red one is already zeroed out, and then this one is still already zeroed out again. So you have some variables still. So this is 1, so that means the red one is already zeroed out, it's lost, and then the other one, this violet color, is still there. So that means all of the variables, they are not going to be retained in your final model. The good thing with LASSO, it helps you to remove all the noise in your data. All the irrelevant features will be removed, and at the end, only the relevant features will be retained. That means it automatically facilitates feature selection procedure. That's the biggest advantage of LASSO over ridge regression. But LASSO has limitations. What is that limitations? So although LASSO effectively handles feature selection, it has limitations. I mean, we have seen that it effectively handles this feature selection procedure, but it has limitations, because when it's trying to deal with correlated features, and we have seen for correlated features, ridge regression is very effective. But in terms of when you have LASSO, when you have correlated features, what LASSO does is, one, it will push one of them to zero, and the other one is retained. The other one will be retained. The other one will be in your model. And this process of one in and the other one out, one in and the other one out, is not really systematic. Is not really very systematic. So for this kind of problem, ridge is effective. So ridge regression is effective in handling correlated features. So LASSO has the biggest problem here. So what you need is you want to take advantage of the two. That means you want to combine ridge regression and LASSO regression. So when you do that, that means you are applying elastic net. So for elastic net, what you do is again sum of square error. That means it's the same for your ordinary least square regression model, but on top of that you have the ridge penalty parameter, and then again you add the LASSO parameter. So that means you are combining two penalty parameters in one, the sum of square error in one regression model. So that means you are applying elastic net. So that means elastic, it gives you flexibility to move between ridge regression and LASSO regression. So this procedure, it creates an effective regularization strategy, and it's an effective because it's a ridge. It's known for being effective, for having effective regularization strategy, and then LASSO is providing effective feature selection method. So elastic net somehow takes advantage of the two models, but sometimes elastic net may not perform as good as LASSO, and LASSO may not perform as good as ridge regression. That's again determined by your data set, and after experimenting again, the no free lunch theorem, you have to try as many models possible, and then you find out which works best for your data. So the implementation for regularized regression model, especially in R, in Python, there are other packages, but since for this tutorial, for this text mining, text classification tutorial, we are mainly focusing on R. So we know that there are additional packages, but package H2, ElasticNet, and Penalized, and then quantitative text models. They also have regularization models mainly for text data, but these are really some of the common packages. But the most common one is GLMNet. That's actually the fastest one. So this is really the fastest one, and I really like this package. I heard it's actually written by one of those guys from Trevor Hastey. Maybe you know the book, this statistical learning. So this I watched some of their talks on YouTube. Maybe you can also find it. And at one time, GLMNet is fast because it's written in Fortran. So some of the packages may be written in C++ or something, or I don't know. So he was mentioning GLMNet package was originally written in Fortran, and Fortran, although now it's almost abandoned programming language, but in this case, it really gave us one of the fastest lightning fast package. Actually, I really love this package. Yeah, so there are other packages, H2O, ElasticNet, and Penalized. I myself have tried this H2O, but H2O requires to connect. So to connect with H2O, with H2O company. So somehow you might find the implementation more difficult. I haven't tried the other models. I have seen the quantitative text models, but I didn't personally implement it. But I do advise. I personally recommend to use GLMNet for its simplicity, and again for its speed. The speed is really fast. You give it a large text data, and then the output is very quick. Of course, that depends on your tuning parameters. So at least for example, for ridge and for ridge regression and for LASSO regression, your tuning parameters are lambda, but for ElasticNet regression, your tuning parameters are alpha and lambda. So the tuning parameters, actually, I have already touched it. The tuning parameter for ridge regression is lambda and alpha. So lambda you could give basically from more than 0 value, 0 point something, until infinity. So you basically try many things. So that means your tuning parameter is lambda, but alpha is set to 0. So that means when you set alpha to 0, you tell your package or the software that you are running ridge regression. And then on top of that, you of course need cross validation. So these are the tuning parameters mainly for ridge. And for LASSO, your tuning parameters are lambda, similar to ridge. So you try multiple values again from more than 0 to infinity, and the alpha value is set to 1. So that means when you set alpha value to 1, you are telling your model that you would like to run LASSO regression. And then again, you need cross validation strategy, tenfold cross validation, or you can do repeated cross validation or something. This is possible with this CVGLMNet function. We will have a look at it later on in the implementation phase. The last one is ElasticNet. So ElasticNet, you have alpha parameter and lambda parameter. So alpha for ridge is 0, for lasso is 1, so the alpha will be between 0 and 1. So infinite number of values you can set from 0 to 1, maybe 100 different values, or maybe 600 different values or something, depending on your machine. So you can set it different values and you can tune it. So anything between, so your model will be anything between ridge and lasso. So when your alpha value is, let's say, 0.5, that means it's at the middle of ridge and lasso. That means it's between ridge and lasso regression. So it's taking half of it from ridge and half of the other side from lasso side. But sometimes when you tune your parameter at the end, your best model may be falling somewhere at alpha 0.2 or alpha 0.9 or something. But that's what I mean. It's like, yeah, what I wanted to say is alpha is set between 0 and 1 in multiple values, and your model tuning process will choose which one is the best parameter for your best model. And again, it requires CVG eliminate, cross validation. It could be tenfold cross validation as usual, or repeated cross validation. That means repeated 3 times, or repeated, I don't know, whatever amount you would like to repeat. But I personally use tenfold cross validation. I don't usually use repeated cross validation, because usually it's a computationally intensive process. So that's all I have for regularized regression. And next time I will talk about more on the implementation. So we will use G-eliminate package, and then we will do the same prediction modeling for COVID and SARS datasets, the text data that I have already been working on the previous sessions. Having said that, thank you very much, and thank you for supporting the channel. And if there is anyone who is interested, please let them subscribe or share it too, or like it. It goes either way. You can also, if you don't like it, you can hit dislike, or if you like it, you can let me know. Thank you. Happy coding.